Hey guys, and welcome to my lecture on the Fourier transform tables. I will cover two tables in this lecture, table of pairs and table of properties. This video is a bit long but absolutely essential to watch as it forms the foundation for the upcoming lectures. Let's start with table of pairs. This table basically includes some common signals and their Fourier transform. We work with these signals very often, and that's why it's really helpful to use the table to travel between time and frequency domains super fast. Here's the table. On the left, you can see the signals in time domain: delta function, 1, rectangular, sinc, exponential, complex exponential, cosine, and sine. On the right, you can see the signal in the frequency domain. So we refer to this table as the table of pairs. In the signal processing books, the table usually includes more signals, and it's a bit longer than this. But I just want to include the signals that are building blocks and absolutely essential. Before I continue, I want to ask you just one thing. Please don't waste your valuable time trying to memorize this table. If you memorize it, it's absolutely useless, and sooner or later, you will be confused and eventually you will give up. So to avoid that, in this lecture, I will cover the proofs for the whole table. Please bear with me, it's gonna be very easy, I promise. As we saw in the last lecture, this integral is called Fourier transform as it helps us to go from time to frequency domain. And this integral is called inverse Fourier transform as it helps us to go from frequency to time domain. So if we have this term, complex exponential, with the negative sign in the power, and the integral here, we can say x of omega is the Fourier transform of xt. On the other hand, when we have this term here and this term here, we can say xt is the inverse Fourier transform of x omega. To prove each pair in the table, you can use either this or this. Let's start with the first pair. If we have delta t in the time domain, the Fourier transform is 1. I'm gonna start with this integral. Let's replace xt with delta function. This function is only non-zero at the origin. So based on the shifting property which I already covered in the elementary signals lecture, we just need to replace t by 0. Exponential to the power of 0 is 1. So x of omega is 1. Before I move on to the next pair, I want to review something with you as it's very important. As you know, when we apply a delta function to an LTI system, the output is called impulse response. During my first lecture on LTI systems, I said ht is the richest response that we can get from an LTI system. Now that you learned Fourier transform, you can fully understand why. Delta function is non-zero only at the origin, but if you look at this signal in the frequency domain, it's 1 everywhere. So if you apply this signal to an LTI system, you are basically stimulating all the frequencies of the system. That's why the response you get is the richest response. So keep this in mind. HT, or impulse response, can fully identify an LTI system as it's the richest response ever. Now let's move on to the next pair. If the signal is 1 in time domain, here's the Fourier transform. As we have delta function here, I prefer to use inverse Fourier transform because then I can use the shifting property. So let's start with this and replace x omega with this signal. 2 pi is cancelled by 2 pi. This function is non-zero only at omega equal to 0. Again, based on the shifting property, we just need to replace omega by 0. So we get 1. That's it. Now, let's look at the first two pairs again to review another main takeaway. If we have delta function in the time domain, we have 1 in the frequency domain. On the other hand, if we have 1 in time, we have delta function in the frequency. Let me plot these signals. Delta t is non-zero only at the origin. In the frequency domain, the signal is 1 everywhere. On the other hand, if the signal in time is 1 everywhere, it's non-zero only at the origin in the frequency domain. These two pairs can perfectly illustrate the inverse relation between time and frequency domains. So here's the main takeaway. There is an inverse relation between time and frequency domains. Let's move on to the next pair. If the signal is a rectangular function in the time domain where capital T is a constant, the Fourier transform is a sinc function in this form. Before I prove this, let's review the definition of rectangular and sinc functions. Rectangular signal, as the name shows, is a window that is 1 from minus t over 2 to t over 2. For instance, for rect t divided by 2, capital T is 2. So the function is 1 from minus 1 to 1. Or rectangular t is 1 from minus 1 half to 1 half. Now let's look at the definition of sinc function. Sinc omega is basically sine omega divided by omega. To find sinc omega t over 2, we just need to replace omega by omega t over 2. Here we go. Okay, let's continue. I'm gonna start with the Fourier transform integral and replace xt with this function. Here is what we get. This window is non-zero only in this interval. So the integral is non-zero only from minus t over 2 to t over 2, where the function is 1. So we get this. From calculus, we know the solution to the integral of e to the power of at, where a is a constant number, is this. This is a, so here is the solution. Let me bring negative sign to the front and replace t by upper and lower bounds. Bring minus sign inside parentheses, here is what we get. From my lecture on complex numbers, we know sine omega can be presented like this. So to use this equation, bring j inside the parentheses. 2 now is missing at the bottom, so multiply bottom and top by 2. Now you can write this as a sinusoidal function. Here we go. Now to use this definition, I'm gonna write the answer in this form. Bring 2 here, it's basically the same thing but different presentation. Now capital T is missing at the bottom, so multiply top and bottom by t. Now we can use this definition. Here we go. This is the final answer. So if we have a rectangular function in the time domain, the Fourier transform is a sinc function in this form. Let's move on to the next pair. If the signal is a sinc function in the time domain where b is a constant, the Fourier transform is a rectangular function. This rectangular function is 1 from minus b to b. The proof here is much easier if you start with the inverse Fourier transform. Then replace x omega with this function and continue. The rest is very similar to the previous example, so please do it yourself to practice. Before I move on to the next pair, let me explain something very interesting. So far, we have seen 4 pairs. Delta function in time, 1 in frequency. 1 in time, delta function in the frequency. Rectangular function in time, sinc function in the frequency. Sinc in time, rectangular in the frequency. This interesting property is called duality, which I cover very soon. For now, just remember, if the Fourier transform of white sheep is black sheep, the Fourier transform of black sheep has something to do with the white sheep. Again, that's called duality. Okay, let's go to the next pair. If we have this signal in the time domain where a is constant, here is the Fourier transform. To prove this, I start from this integral and replace xt with this signal. U of t, or a step function, is 0 before 0 and 1 after that. So the integral is non-zero only in this interval, and therefore we get this. Let's combine these two terms. Again, based on the remark, this is the constant value and the solution is this. I'm gonna bring minus sign to the front and replace t by upper and lower bounds. E to the power of minus infinity is 0 and e to the power of 0 is 1. Bring the minus sign inside the parentheses. Here is the final answer. I'm just gonna switch these two terms and write it like this. Done. For the next pair, we have a complex exponential function. Here is the Fourier transform. Since we have a delta function in the frequency domain, I'm gonna use inverse Fourier transform to take advantage of the shifting property. Let's replace x of omega with this function. Here we go. 2 pi is cancelled by 2 pi, this function is non-zero only at omega equal to omega naught. So based on the shifting property, we just need to replace omega by omega naught. Here is the final answer. Done. Now let's look at this pair again and try to understand what it means. As I already mentioned, think of frequency as colors. Here we just have one frequency, omega naught. This means the signal has just one color. That's why in the frequency domain, we have a delta function which is non-zero only at omega naught. Again, our signal in time has just one color. That's why the frequency content is just non-zero at one point. Before I move on to the next pair, let me clarify one point. Here I found the Fourier transform for this complex exponential function, which is a periodic signal. Now you might say, Iman, wait a second, what the hell are you doing? As we already learned, for periodic signals, we need to use Fourier series to go to the frequency domain. And for non-periodic signals, we should use Fourier transform. So you might ask, how come I found Fourier transform for a periodic signal? Here's the short version of my defense. In the previous lecture, I drew this picture. As you can see, the Fourier transform monster is eating the Fourier series baby monster. This basically means Fourier transform includes Fourier series, and you can find Fourier transform for a periodic signal. I will dedicate one full lecture to this topic, but for now, if you are curious to know why, let's consider this non-periodic signal, which is only non-zero from -1 to 1. Now think about it. You can say this signal is basically periodic, but the period is infinity. So each non-periodic signal is in fact periodic, but the period is infinity. That's why you can have Fourier transform for periodic signals as well. I will talk more about this in the near future. Let's go to the next pair. If we have cosine function in the time domain, here is the Fourier transform. To prove this, I go with inverse Fourier transform equation and replace x of omega with this. Here we go. Pi is cancelled by pi. Let's break this integral into two integrals. This function is non-zero only at omega naught, and this one is non-zero at minus omega naught. Based on the shifting property, we just need to replace omega by omega naught here and by minus omega naught here. We know cosine function can be expressed in this form. So let's factor 2 at the bottom. This is cosine function. So here is the final answer. Done. The last pair in the table is this. The proof is very similar to the one that I just did for the cosine function. So please do it yourself to practice. Okay, we are done with the table of pairs. Now I want to talk about table of properties. First, let me explain why this table is useful. Let's assume we have this pair. Basically, we know signal in time and frequency domain. Now the question is, if we tweak the signal in time domain, what's gonna happen to Fourier transform? Or the other way around, if we tweak the signal in the frequency domain, what's gonna happen to the signal in time domain? Table of properties helps us to answer these questions fast. Let's assume we have this pair as the starting point. Now, if we shift the signal in time domain by t naught, we need to multiply x of omega by this complex exponential function. This property is called time shifting property as we shift the signal in the time domain by t naught. If we multiply the signal in time domain with this complex function, the signal in the frequency domain gets shifted by omega naught. This is called frequency shifting property as we shift the signal in the frequency domain by omega naught. Please note that for time shifting property, t naught is constant and omega is the frequency variable. On the other hand, for frequency shifting property, omega naught is constant and t is the time variable. If we scale time by a factor of a, the signal in the frequency domain gets scaled by a factor of 1 divided by a. This property is called time or frequency scaling. As you may remember, in my first lecture on the frequency domain, I intuitively explained the inverse relation between time and frequency domain. This property exactly shows the same point. The next property is called time domain differentiation, as we apply derivative to the signal in time domain. The next property is called frequency domain differentiation, as we apply derivative to the signal in the frequency domain. Convolution in time domain is multiplication in the frequency domain, and multiplication in time domain is convolution in the frequency domain. And here's the conjugation property. The next property is called duality, which is super interesting if we have this signal in time domain, which basically means the same shape, but instead of omega, t is the variable. Here is the Fourier transform. The next property is called time domain integration, as we apply integral to the signal in the time domain. Again, you don't need to memorize this table at all. Please don't even try. The proof for all these properties is super easy and straightforward. Let's do it together. To refresh your memory, this is called Fourier transform and this is inverse Fourier transform. If we have this complex exponential with the negative sign in the power and this integral, we can say x omega is Fourier transform of xt. If we have this complex exponential and this term here, we can say xt is the inverse Fourier transform of x omega. To prove different properties, sometimes it's easier to use this integral and sometimes this one is better. But no matter which one you choose, the result is always the same. Let's start from the time shifting property. To prove this, I prefer to use inverse Fourier transform. Now let's replace t by t minus t naught. Here's what we get. Let's break this term into two exponential functions. Here we go. And finally, let's move this term to the front. This is equal to xt minus t naught. Now look at this integral again. We have this complex function here and this term here. So we can say this is the inverse Fourier transform of this signal. That was the proof for the time shifting property. Now let's look at the frequency shifting property. To prove this, I prefer to use Fourier transform integral. Now let's replace omega by omega minus omega naught. Here we go. Break this term into two exponential functions. Bring this one to the front. Now look at this one carefully. We have this complex exponential function with negative sign here and this integral here. So we can say this is Fourier transform of the signal here. Done. Before I continue to the next property, let's understand the meaning of time and frequency shifting property. Let's start with this one. As I explained before, I like to see frequencies as colors. Now, if we shift the signal in the time domain, based on my lecture on the signal transformations, the signal shape is basically the same, just we start sooner or later. This means the time shifting does not change the colors. And that's why we still have x omega here. But to start sooner or later, we need this complex term. To visualize that, let's consider a point in the polar system. If we want to have the same radius but start from somewhere else, we just need to change the phase. In the polar system, this means multiplication with a complex exponential function. If you don't get what I just said, please watch my tutorial on the complex numbers. Now let's look at the frequency shifting property. If you consider this frequency as a specific color, by multiplying this term with xt, you are basically adding a new color to all existing colors in xt. That's why the whole color or frequency spectrum is shifted by omega naught. Again, just to visualize this property, imagine a new color is added to all existing colors. Let's move on to the next property. This is called time or frequency scaling property. To prove this, I'm gonna use inverse Fourier transform. Let's replace t with at. Here we go. Now let's change the integral variable. I'm gonna replace omega a with k, which means replacing omega with k over a. Apply derivative to both sides. Here's what we get. When we change the integral variable, we also need to change the interval. To do that, I'm gonna consider two scenarios. In the first scenario, A is positive. In this case, when omega is minus infinity, k is minus infinity multiplied by a positive number. So k is minus infinity too. When omega is plus infinity, k is also plus infinity. In the second scenario, A is negative. In this case, when omega is minus infinity, k is minus infinity multiplied by a negative number. So k is plus infinity. When omega is plus infinity, k becomes minus infinity. So for the first scenario, after replacing omega a with k, we get this. And for the second scenario, we get this. As you know, when a is positive, we can say a is equal to its absolute value. In fact, absolute value has no impact on a positive number. On the other hand, when a is negative, a is equal to minus 1 multiplied by its absolute value. Here is an example. The absolute value makes a negative number positive. Now let's use this simple property. For the first scenario, when a is positive, I'm going to replace a with its absolute value. And for the second scenario, when a is negative, I'm going to replace it with this term. As we know from calculus, minus 1 multiplied by the integral from b to a is equal to the integral from a to b. In fact, you can use the minus sign to switch upper bound with the lower bound. Now let's bring minus sign here and switch the interval. Here is what we get. Now we can see the integral in this scenario is exactly equal to this scenario. So no matter if a is positive or negative, we can have just one expression. The integral variable k is just a name. You can call it whatever you want. I'm going to call it omega again, and I'm going to bring this to the front. Here we go. Again, I'm replacing all k's with omega. Now look at the result. We have this complex function here and this term here. So we can say this signal is the inverse Fourier transform of this term. Done. This property shows the inverse relation between time and frequency domain. For instance, when a is 2, we get this. x2t means we play signal 2 times faster. So it takes less time to finish, and that's why the signal gets compressed in the time domain. This results in expansion in the frequency domain. Another example, when a is 1/2, we get this. This transformation means we play signal with half a speed, so it takes more time to finish, and that's why the signal gets expanded in the time domain. This means compression in the frequency domain. So keep this in mind. There is an inverse relation between time and frequency domain. Let's move on to the next property, time domain differentiation. To prove this property, I'm going to use inverse Fourier transform integral. Now apply derivative to both sides with respect to t. As we know, the derivative of this function, where a and b are constant, is this. Here we are applying derivative with respect to t, but this is a function of omega and independent of t. So you can treat this term as a and also this term as b. So by applying derivative, we get this. Move this one to the front. Here we go. Now we have this complex function and this term here. So we can say this signal is the inverse Fourier transform of this term. Done. This property is super useful to simplify and solve complicated differential equations. Differential equations can be found almost everywhere in science. For instance, in physics, wave equation, heat equation in thermodynamics, shallow water equations, and tons of other equations are all described by differential equations. In chemistry, you can find differential equation. For example, the rate law for a chemical reaction is a differential equation that links a speed of reaction with the pressure and some other stuff. Believe it or not, differential equations are commonly found even in economics. So they are everywhere, and this amazing property helps us to solve them. Now let's intuitively understand the meaning of time domain differentiation property in signal processing. By applying derivative in the time domain, we get j omega in the frequency domain. This means derivative can be seen as a high-pass filter. Let me explain why. Let's say xt is constant or the frequency is 0 as the signal is not changing. By definition, a high-pass filter does not pass low frequencies. Now look at the frequency side. When omega is 0, 0 multiplied by x omega, we get 0. This means x cannot pass from this filter. On the other hand, let's assume xt has high frequency components. By definition, high frequencies can be passed or amplified by a high-pass filter. Now let's look at the frequency side. When omega is a large number, we are in fact amplifying x omega. So to recap, differentiation in time domain acts like a high-pass filter. As we will see later in this tutorial, integration in time domain acts like a low-pass filter. Let's move on to the frequency domain differentiation. To prove this, I'm going to start with the Fourier transform definition. Now apply derivative with respect to omega. Xt is a function of t and independent of omega. So when we apply derivative with respect to omega, we can treat xt as a constant. Here's what we get. To get rid of j here, let's multiply both sides by j. As you know, j is the square root of -1. So if you multiply these two, we get -1, which is cancelled by the minus sign here. Let me write it again. Bring t to the front. Now we have this complex function here and this integral here. So we can say this is the Fourier transform of this term. Done. Next property is time domain convolution. Convolution in time is multiplication in the frequency domain. I explained the convolution concept when I was talking about LTI systems. So to understand this property, let's consider LTI systems again. When xt goes through an LTI system, the output is basically xt convolved by the impulse response. Also, as I explained in the Fourier series lecture, when a complex exponential function with the frequency of omega goes through an LTI system, the output is basically the same multiplied by the frequency response at that frequency. Now, because the system is linear, if you multiply the signal in time domain by x omega, the output gets multiplied by the same value. Again, because the system is linear, a linear combination of inputs results in a linear combination of outputs. Let's also multiply the input by 1 over 2 pi. The output is multiplied by the same value as the system is linear. Now look at this integral carefully. This is basically xt based on the definition of inverse Fourier transform. But we already know if xt goes through an LTI system, we get this convolution at the output. What does this mean? The input to the LTI system at the top and at the bottom is the same, i.e. xt. This means the outputs must be the same. Or we can say this integral is equal to the convolution between xt and ht. Let me write it again. Convolution is equal to this integral. I'm going to bring h omega here. Now we have this complex function here and this term here. So we can say this convolution is the inverse Fourier transform of this multiplication. That was a simple proof for the convolution property. In this property we have x1 and x2, but here we have x and h. It doesn't really matter if the name is x, h, x1, x2 or whatever. That's just a name. The main takeaway is convolution in time domain is multiplication in the frequency domain. This simple property forms the foundation of filtering. If we want to reject a specific frequency, we just need to set h to 0 at that frequency. Or if we want to pass a specific frequency, we just need to set h to 1. I will talk about filtering again in the upcoming lectures. Let's move on to the frequency domain convolution. Multiplication in the time domain is convolution in the frequency domain. This property is used in sampling to go from continuous to discrete domain. In fact, sampling or Nyquist rate, which is a fundamental bridge between continuous and discrete signal, is derived from this simple property. I will dedicate one full lecture to sampling and will talk about this property more in the future. Next property is conjugation. To prove this, I prefer to start from the Fourier transform definition. Apply conjugate to both sides. To apply conjugate to a complex exponential, just switch the power sign. So here's what we get. Now, if we want to use the Fourier transform definition, the complex function must have the negative sign in the power. So to get that, let's replace omega by minus omega. Here we go. Now we can use the Fourier transform definition. We have this complex function here and the integral here. So we can say this signal is the Fourier transform of this function. Done. The next property is duality. If Fourier transform of xt is x omega, the Fourier transform of capital Xt is 2 pi multiplied by a small x of minus omega. This is very interesting. If the Fourier transform of a small x is capital X, the Fourier transform of capital X has something to do with the small x. To prove this property, I'm going to start from inverse Fourier transform definition. Then I'm going to use very simple tricks. First, let's replace omega by k. The integral variable is just a name. You can call it whatever you want. So we get this. For xt, let's replace t by minus omega to have fun. Here we go. Now let's replace k by t to have more fun. Here we go. Then multiply both sides by 2 pi. 2 pi is cancelled by 2 pi. Let's write it again and switch the order of these two. Now we have this complex function with the negative sign in the power here and the integral here. So we can say this is Fourier transform of this signal. Done. This property is super interesting and useful, as we will see in the next tutorial. Last property is time domain integration, which I will prove in the next tutorial as an example. For now, let's try to understand the meaning of this property. Integration in time domain is 1 over j omega in the frequency domain plus this term. Integration in time domain can be seen as a low-pass filter. Let me explain why. By definition, a low-pass filter passes or amplifies low frequencies and rejects high frequencies. Now, when the frequency is low, this term is high as omega is at the bottom. So x omega is amplified. On the other hand, when the frequency is high, this term is low and x omega is rejected or weakened. So keep this in mind. Integration in time domain acts like a low-pass filter. Okay, that's all I want to say for this lecture. Thank you so much for watching this tutorial on Fourier transform tables. I know it was long, but it was absolutely essential to understand the meaning behind the tables. In the next lecture, I will solve lots of examples on how to use Fourier transform tables. Here's what I promise. After you're done with the next tutorial, you can call yourself Fourier transform expert, and no one even dares to challenge you on this topic. You have my word for that. Thanks again for watching. Don't forget to subscribe and see you guys in the next video.